Greetings everyone, I am Siddhant Engineer and this website has been created by the combined efforts of Meet Chheda, Virendra Singh Khuman, Siddhant Engineer and Shubh Arora. We have implemented 4 simulations for 4 algorithms pertaining to different topics in operating systems. The first one is shortest job first algorithm, which is used to schedule jobs in a system. Next one is a dynamic philosopher problem, which implements the concept of how multiple tasks can be concurrently executed. Next one is a loop algorithm, disk scheduling algorithm, and the last one is first come first serve, a page scheduling algorithm. We began our project with a simulation of shortest job first algorithm. Shortest job first is a task scheduling algorithm which is used for the process of allocating system resources to many different tasks by an operating system. Shortest job first is a scheduling policy that selects the waiting processes with the least execution time to execute next. It is an example of a greedy algorithm. In our simulator, we enter various processes which are denoted by a unique index ID, and the user enters the arrival time and burst time or execution time of various processes. The clock starts from 0 and adds process to the waiting queue as their arrival time hits. Once the process enters the waiting queue, our scheduler opts to decide for the task with the least execution time. We can have a look at the output and the order in which the task order. We can observe from the Gantt chart that at time t is equals to 0 there are no processes, so it's empty. At time t is equals to 1, p1 is pushed into the waiting queue and executed since there are no other processes in the waiting queue. Since it has a burst time of 5 seconds, 5 seconds are elapsed on the timer as well. Till that time, all other processes have been pushed into the waiting queue. Now, at time t is equal to 6, there are 4 other processes in the waiting queue. Since the process P4 has the least burst time, it is executed right away. In a similar way, rest of the processes are executed. This algorithm helps us to procure the minimum average waiting time amongst all algorithms. However, shortest job first is unfortunately not feasible, as operating system may not know burst time beforehand, but it can be brought to use in a specialized environments where accurate estimates are available. And by clicking on the download button, we can get a copy of our table.
Let us go through the dynamic philosopher's problem. The dynamic philosopher's problem is a classic synchronization problem wherein there are 5 philosophers sitting together at a dining table and there is some food placed at the table. There are 5 forks, one between each 2 adjacent philosophers, as you can see on the screen. There is also the status of each philosopher shown, which can be either of 3 things: eating, waiting, and thinking. Eating is the state when the philosopher has access to both forks and then he is able to eat. When he has access to only one fork, the philosopher must wait, that is the waiting state, for some other philosopher to drop a fork so that he can get access to the second fork and start eating. Thinking state is the state in which the philosopher doesn't want to eat at all. Now, in terms of operating systems, this problem involves multiple processes sharing a limited set of resources in order to perform a particular task. Here the multiple resources are the forks, the multiple processes are the philosophers, and the task being performed is of eating. One crucial challenge in this problem is of deadlocks. Deadlock is the state in which all philosophers would be having one fork and would have to wait possibly infinitely for the second fork. However, we have handled this scenario quite well and we will go through that shortly. Now, to solve this problem, we have used semaphores. A semaphore is a variable used to control access to common resource by multiple threads and avoid critical section problems. On clicking the simulate button, now we are able to see that whenever a philosopher has two forks, he is able to eat and the color changes to purple. And also the state of Aristotle, Confucius, etc. changes to eating when they have two forks available and shifts back to thinking when they have done the process of eating.
The third segment of our project is a disk scheduling algorithm. The disk scheduling algorithm that we implemented is the Look disk scheduling algorithm. A disk scheduling algorithm processes the I/O requests that are entered in a disk. In the Look disk scheduling algorithm, our simulator first asks the user to enter a head index. Then it asks the user to enter a few process indexes. Then the user also selects a toggle based on if they want to run the Look algorithm or the Clook algorithm, and if they want to go to the values to the right of the head index, these are values greater than the head index first, or the values lesser than the head index, which are the values to the left first. Once the user has done that, the user clicks calculate, and then we can see how a graph and a table display the output in which the processes are executed. The graph has been imported through using an extension called Plotly.
The fourth segment of a project involves a page scheduling algorithm. These algorithms are primarily used in memory management and caching. We have implemented a simulation of the first in first out replacement algorithm. This algorithm determines which page will be replaced in enough frames when new page enters based on the order of the arrival of these pages. We first enter a capacity. The capacity refers to the number of frames in the actual physical memory. We then enter page indices. Once we click the calculate button, we can see via the matrix how the pages are stored in the actual physical memory. Every time a new page that has not yet been loaded into the physical memory appears, the output showcases a miss or a page fault. In such a case, an oldest page gets replaced by the new page. The first in first out algorithm is the simplest and removes the oldest page from the queue when the frames are already filled. If the page was already existent in the physical address, then the frames do not change and we can see that the output metric shows us a hit.
Implemented a feature in all of our simulations that we believe enhances the user experience and makes our website a notch better. We have given a user to store the data they have been able to calculate on their own devices with a feature to download the arrays of the calculation they've managed to create and the graph they have constructed. We believe that this adds to the user's learning experience in regards to them being able to keep the learnings on their own devices as well.